Have you ever been sitting in an aeroplane, somewhere over the Atlantic, when the pilot's voice comes over the intercom to tell you that you're cruising at 500 and something knots at 30,000 feet? You nod along. You glance at the window. And then, almost immediately, you realize you have no idea what that actually means. 500 knots. Is that fast? You know what 500 miles per hour feels like as a concept. But a knot? You have a vague sense that it involves the sea. Maybe rope. You're not sure why a pilot hurtling through the stratosphere in a machine made of aluminium and jet fuel is using a word that sounds like it belongs on a fishing boat. Your brain files it away as one of those things aviation people say, the same way doctors use Latin and lawyers use Latin, and apparently pilots use the vocabulary of someone who died at sea in the 1600s. Here's what makes this genuinely strange. Every commercial aircraft in operation today, every cargo ship, every naval vessel on every ocean, and every Coast Guard helicopter uses this unit. The entire global system of navigation, worth trillions of dollars in trade and responsible for the safe movement of billions of passengers every year, runs on a measurement invented before anyone had ever seen a steam engine. But here's the surprising truth. The knot wasn't an accident of history that nobody bothered to update. It's a unit of measurement so precisely fitted to the geometry of the Earth that switching to anything else would actually make long-distance navigation harder, not easier. Today, we're unraveling why sailors invented the knot, what rope and sand have to do with the speed of a jet aircraft, and why this ancient unit turns out to be more scientifically elegant than anything we've come up with since. To understand the knot, you have to first understand the problem that created it. For most of human history, the most dangerous question a sailor could face was a simple one. Where are we? On land, you could look at landmarks. You could ask someone. You could follow a road. On the open ocean, there was nothing. No landmarks, no roads, just water in every direction, and beneath it, reefs and shallows that could destroy a ship in minutes. Sailors developed a technique called dead reckoning to stay alive. The idea was straightforward in principle. If you knew where you started, and you knew your direction, and you knew your speed, you could calculate your position at any moment. Direction was manageable. A compass gave you that. Starting position was manageable. You knew which port you left from. But speed was the problem. The ocean has no mileposts. There is no way to look out at open water and see how fast you're moving. For centuries, sailors guessed, they timed floating debris drifting past the hull. They estimated based on the feel of the wind. Their calculations drifted, and ships drifted with them, and some of those ships were never seen again. By the 17th century, as European trade routes extended deeper into the Atlantic and further into unfamiliar waters, the problem of measuring speed at sea had become urgent enough that someone had to solve it properly. The solution they arrived at was called the chip log, and it was a piece of engineering so simple it almost feels like a joke until you understand the mathematics locked inside it. Think of it like a fishing line with a float, except that the float is designed to stop dead in the water while the boat keeps moving. A wedge-shaped piece of weighted wood was thrown overboard from the stern of the ship. Because it was weighted at the base, it stood upright in the water and, crucially, stayed almost perfectly still as the current took it. The ship moved forward, and a coiled rope attached to the float began to unspool from the deck. Tied into that rope, at precise intervals, were physical knots, actual loops in the hemp. A second sailor held a sand glass, a timer of fixed duration, and the moment the wood hit the water, the glass was flipped. As the rope ran through the first sailor's fingers, he counted the knots passing through his hands. When the sand ran out, the count stopped. The number of knots that had passed in that fixed time was the ship's speed. In knots. The word never left the language, but the interval between each knot in the rope was not chosen at random, and this is where the history of a sailor's tool becomes the science of the earth itself. A statute mile, the kind used to measure road distances on land, traces its origin back to ancient Rome. Roman soldiers measured distance by counting paces, and 1,000 double paces, roughly the length a soldier's foot traveled in a complete stride cycle, gave you something close to what we now call a mile. It's a unit of distance built around a human body walking. You cannot walk on the ocean. So maritime navigators built their own system from the ground up, and they built it around the shape of the planet instead. The Earth is a sphere. A sphere can be divided into 360 degrees of arc. Each degree of latitude, the lines that run parallel to the equator, can be divided into 60 smaller units called minutes of arc. Sailors decided that 1 nautical mile should equal exactly 1 minute of latitude. This was not arbitrary. It meant that a navigational chart and a ruler were the same instrument. A captain looking at a sea chart could measure distance directly against the latitude lines already printed on it. No conversion required. The map spoke the same language as the measurement. The rope knots were spaced at precisely the interval that made the timed count equal the speed in nautical miles per hour. The unit was not named after the tool. The tool was built to produce the unit, and the unit was built to fit the Earth. So, if this system was invented for wooden ships crossing the Atlantic, why is it still the standard unit inside the cockpit of a modern passenger jet? The answer, as is often the case in history, comes down to what was already there when aviation arrived. The first long-distance flights were over oceans. There were no aeronautical charts because there had never been a need for them. What existed in abundance were maritime charts, built on the nautical mile, calibrated to latitude and longitude, already trusted and proven over centuries of navigation. Early aviators crossing the Atlantic, navigating by the same stars in the same horizon that ship captains had always used, simply adopted the tools that were already there. But there is a deeper reason the unit survived into the era of GPS and fly-by-wire computers. Over long distances, the curvature of the Earth is not negligible. A flight from London to Tokyo is not a straight line on a flat map. It is an arc across a sphere, and calculating that arc accurately is far simpler when your unit of speed is already defined in terms of the Earth's own geometry. 1 knot is 1 minute of latitude per hour. The planet and the instrument speak the same language, and changing the instrument would mean teaching them a new one for no practical gain. So, the next time a pilot announces your cruising speed in knots, and the number means nothing to you, you'll know that it isn't jargon. It's a message written in the geometry of the Earth, passed from a sailor throwing a weighted log into the Atlantic 4 centuries ago to the flight computer calculating your position over the same ocean right now. The unit survived not because nobody thought to replace it, but because it was built around something that doesn't change. Speed is temporary. The shape of the planet is the measurement.